everyone. This is Reem Mohammed, a PhD student at UNSW Canberra. I'm presenting my paper, Communication Constraints on Swarm Guidance Tasks. This is a collaborative work with my supervisors, Dr. Saber, Professor Robert, and Professor Hussein. Are you watching World Cup?
Yes.
If, God forbid, something bad happened or a disaster in the stadium, how can we manage guiding the people to the safe areas without putting stress or danger on the riskers? Shepherding is one well-studied example of crowd management. So today I'm going to describe autonomous shepherding, show the role of communication on autonomous shepherding, show the research question and proposed methods, then describe the main results, then drive conclusion and future directions. As I said, that shepherding is one important method of crowd management. In that case, autonomous agent acting as a sheepdog may affect the sheep and putting pressure on some points, namely herding points, so that they can move from one point to another. This has been proven to be less stressful on sheep than using a biological sheepdog. However, autonomous systems are known to have limited view range and also limited battery life. So we modeled the system by using a central unit that is responsible for observing the change in dynamics of the sheep in real time, to find the optimal points for the robotic sheepdog to head to put pressure on the sheep so that they move from one point to another in a limited time. It sends this information through a wireless communication channel. Then the robotic sheepdog will receive this information and head to these points whenever they are received. However, in challenging environment, wireless communication channel suffers from high level of noise. This will lead to inaccurate information received at the sheepdog and then cascades in task failure. Our main focus in this work is to improve the quality of the transmitted data so that we can improve the success rate of the shepherding task. We all know that a wireless communication signal, the power of it degrades as the distance increases. So for short distance, the signal power to the noise power can be relatively high, which is SNR. In that case, the receiver can accurately receive the data and go to the accurate herding points. However, when the distance is large, the SNR goes low. And in that case, the receiver will not be able to interpret the accurate locations. In shepherding task, the shepherd needs to move throughout the time in order to put pressure on the sheep to move them from one point to another. When the distance increases between the central unit and the shepherd, it will not get accurate information. So the main research question now is, how the transmitter, which is the central unit, ensures high success rate of the transmitter to the sheepdog, which is the receiver, under the effect of high stochastic channel. We thought about two different scenarios. The first one is that the central unit is stationary. In that case, it's not consuming any energy in mobility, but it is at risk of high level of loss in transmissions. While there is another case is that the central unit is fully mobile and it is moving exactly with the same velocity as the sheepdog. In that case, it's energy expensive, but it leads to high success rate in transmissions. To address this trade-off, we have the following aim: finding the sufficient speed for the central unit so that it ensures high success rate in transmissions while not consuming too much energy in mobility. So we used Markov decision process to model this problem, where the actions represent discretized velocity for the central unit, where A0 is the lowest velocity and A4 is the highest velocity. Since the distance between the shepherd and the central unit is the most effective part in the transmission success, so we consider this distance as the states. Then we proposed a very simple method, which is called incremental search. In that case, the central unit will choose to move with the lowest velocity, A0, do the transmission. If it fails, it increases it to A1, do the transmission. If it fails again, and so on, until it reaches a point that the transmission succeeds. Then it goes back to A0. Then we incorporated the use of Q-learning in this. We used the Q-learning to create a table at the central unit, the Q table, where the states are the distances and the actions are the velocities, where transmission succeeded or not. So we used we proposed two different reward functions that are both function in the energy consumption in mobility and the success rate of transmission. For the second reward function, we also consider the level of error. So let's assume a scenario where the distance between the central unit and the shepherd is S2. It makes the transmission, and then if the transmission fails, it has very small Q value due to this reward, very small reward or zero reward. Then it increases the velocity to A1. If the transmission fails again, it increases it to A2. If the transmission succeeded, now it has bigger reward stored in this Q table. So if this case is repeated again in the future, it will help getting better decision about the velocity so that the transmission succeeds. So now we have two different reward functions. We call it Q1 and Q2. And then we use the incremental search so that we can initialize the values in the Q table, which is a conservative way for energy, where the action with the lowest velocity has the biggest Q value initially, and the one with the lowest velocity with the biggest velocity has the smallest Q value. We can see now we have IS3, IS1, which means that the actions are taking initial values 0.1, 0.09, 0.08 until 0.05 for A4. This is a small gap between the Q values for each action. While for the IS3, we make the gap better between the Q values for the same state and different actions. We studied this case when the central unit is moving. But for finding the optimal locations for the shepherd, how can we do that? We used SOHP that was proposed in 2021, where the central unit was assumed to be stationary and the communication channel is assumed to be noiseless. SOHP-N refers to the case when SOHP is used but the noise is introduced. In these two cases, the central unit is stationary, and all the cases of Q1 and Q2 and versions, the central unit is moving with the velocity that is determined based on the algorithm. Then we tested our scenario on 25 episodes for 50 sheep initialized at 3 different initial densities. That is characterized by K in the second column. When K is equals 1/2, it's the smallest value. It means that the density is the highest, which means that the difficulty is the lowest because the sheep is initially very close to each other. While for K equals 3/4, it means that the density is very low, which means that the difficulty is the highest. We can see that in the column 3 and 4, you can see here that the success rate for SOHP with noiseless channel is 70, while when there is a channel noise, it goes to almost its half in all the 3 cases. And for the other columns, it shows that when the central unit is mobile, it improves the success rate of the task within a limited time. So you can see, for example, here in the first row, when K is equal to 1/2, the success rate even improved than the case when the channel was assumed to be noiseless. So now let's see a scenario where The central unit is using Q1IS3, and it is the magenta one here, initialized at 300, 300. The shepherd is the green triangle here, and the sheep are the small green triangles with edges representing their limited view range are in yellow. The final path that was sent is in green, and these the paths that are sent, but not the accurate paths that are received. The final paths that are received are in red, which is the shepherd will be following through time. The sheep are initialized in this circle with k equals 1/2, which means that they are in the closest case to each other. So let's see what happens. We can see that the central unit is following the sheepdog, but with less velocity. And the sheepdog is able to succeed in its task in a limited time. To summarize, reinforcement learning is efficient in coping with channel noise without modeling the channel. This encourages us to merge it with our proposed model, IPCL, the collaborative deep learning method for minimizing the effect of channel noise. The performance of both Q-learning versions is satisfactory, with initialized with bigger gap between the Q values of the actions. This can be analyzed further under the effect of different channel models. Third, the reward value is not correlated with the success rate, since the large number of retransmission lead to accumulated higher reward value despite the less probability of success. So this means that improving the reward function by considering penalizing retransmission may be useful. Finally, real-time learning without training phase may provide good results, but not high stability. So, using deep neural network may improve the stability, but the training time should be considered to be limited in such dynamic tasks. Thank you so much for your time. Any questions?
Anyone have any questions?
I have a couple of questions. Well, I really appreciate your presentation. It's really a great presentation. And well, I was thinking that there are already very good algorithms in comparison with Q-learning algorithm. So I was thinking what are the reasons that you decided to use Q-learning rather than going for example, let's say DQN, because both of them are like value-based algorithms, right? So they pretty much work in a similar way, but DQN has like deep learning, and then that's how it has been, getting better compared to Q-learning algorithms. So I was wondering, why you choose this Q-learning algorithm rather than DQN or other algorithms?
Yes, or also actor critic. That's also another question.
Right.
I agree. But can you see that I didn't use any training?
Mm-hmm.
So in that case, if you use deep learning, you always need training. But in such dynamic tasks like shepherding, you don't know where the environment will be and how it would be. Now I give an example in a stadium. Yes, this is a predictable environment that you can do some testing on. But in case of, let's say, fire, everything is changed. So you don't have really the data for training. In other case, if you're doing, for example, there is a fire enforced and you want to manage it with other swarms that are physical systems. In that case, also you don't have enough training data or even any training data. So online learning would be better with reinforcement learning. That's why in the future direction was how can we make this with, let's say, one-shot learning or something like that.
So
important question, thank you.
What was the extent of, when you were formulating MDP? So was there something like state? Because I noticed you have defined the actions, right? So what about the state of the environment?
Yes, also I define the states as distances, since distances are the most effective part in this communication model that I used, so that's why it is defined by distances. However, if I use different communication model, maybe defining states should be changed. If I use some other metrics, so this state definition also could be different.
Also same thing. So you have a set of actions, and then those set of actions is actually the velocities, right?
Yeah.
So is there any context or situation where you have like, you have to dynamically define the set of actions? You got my point? Like,
yes.
For example, you have like 5 elements in the set of actions.
Yeah.
And then, but in some context, you only have like less than 5, probably 3 velocities are possible in certain actions. If there is this situation, how are you going to handle this?
Yes, this is very interesting. First of all, having limited number of actions is so much realistic. Do you know why? Because physical systems always have maximum velocity. They cannot exceed it. So it's realistic in this regard. However, how about that you always discretize the difference between maximum and minimum and divide it by the number of actions that you have. So you always have numbers in between, right? Right? So you don't have to worry much about having only 3 actions in one case or 2 actions. This is not the fact. You can always have numbers between 2 numbers and have 5 of them. Yeah.
Thank you.
You're welcome.
It's a very good talk.
Thank
I
you.
was just wondering, in your MVP, did you have to choose any parameters? Do you have any parameters in your model that required to be tuned for the current scenario, or was it totally permittless?
I don't understand exactly what do you mean by parameters. Can you give me an example?
So, in case if you had to define any probability distribution from where you have to sample in order to decide where your next step is.
Have probability distribution for what exactly? Because now I am only considering 2 trade. If you can remember, I have 2 trade-offs: the velocity and the transmissions. The most important factor in transmission is
it all
distance.
Is it always deterministic, your scenario?
In that case, it's deterministic, but of course it doesn't have to be like that. This is maybe a really good extension that you can make it more probabilistic. That's true. Yeah.
Because if it's probabilistic, then you can, I don't know, have some prior or on what you think you should go, because you never know if it's going to be a wrong decision in case if the environment has some uncertainties.
The environment already has uncertainties, but if you can see now that already the Q value that is obtained is always considering alpha max and all these things. So it's always considering also it's a probabilistic solution. It never, for example, let's say in the example that I demonstrated, this one give the maximum reward, right? But if this happened, it just has a higher probability to be selected, but it's not a must that it will be selected. Yeah. That answers your question?
Yes, thank you.
All right, you're welcome.